Hi, I'm Kshama Lakshmi Ranganatha, a grad student at Boise State University, here to present a wireless multi-channel printed capacitive strain gauge system for structural health monitoring. Before diving deep into this presentation, I would like to go over softgoods. Softgoods are high-strength fabric that are flexible and lightweight. These materials are extensively used in the space industry for construction of inflatable space structures like spacesuit or space habitat systems. Using these materials lowers the construction and launching costs, and also the structures that employ soft goods have minimal mechanical components, making them less complex and highly reliable and durable. Given the benefits, how do we actually account for the safety and structural integrity? That is done through structural health monitoring. Conventional structural health monitoring systems designed for large structures like the bridge or an airplane, but these structures are made from rigid materials like steel. But we established before that inflatable space systems use soft goods. Also, NASA uses Kevlar stuff, a type of soft goods that is known to tolerate high amounts of loads for their construction. So the idea here is to have multiple strain sensors on the straps. So with multiple strain sensors, we will have continuous strain monitoring that helps in the diagnosis to detect or locate damage or any kind of anomaly on the structure, sending emergency notifications, which in turn enables smart EDL or entry, descent, landing operations if needed. We established we need strain monitoring. Strain monitoring is done through strain gauges. Commercially available strain gauges are resistive in nature, and they are proven to have long-term device failure. They're sensitive to temperature given the extreme conditions of space. It's not a good idea to use resistive strain gauge. Also, due to the sensitivity, they exhibit hysteresis. They're also relatively stiff and have high material waste in their production. Therefore, to compensate for their drawbacks, we recently proposed an aerosol jet printed capacitive strain gauge. These employ interdigitated electrodes that have multiple parallel plate capacitors in series, and they prove to have excellent performance, good gauge factor of 5.2. They can be manufactured on site or in space, and they're highly durable and flexible. But the one drawback is that their intrinsic capacitance or their resting capacitance range is from 42 picofarad to 15 nanofarad. This large variation is due to the printing process variation, but does not hurt the overall sensor performance itself. So the main motivation for our system is that we have a capacitive interface and also the large intrinsic capacitance variation. So we need a system that not only takes these two factors into account, also we need something for distributed strain sensing that's low cost, easy to assemble in space if the sensor breaks down, and also sizable to the Kevlar straps. So therefore, we present a wireless multi-channel structural health monitoring system. So here's the concept of our structural health monitoring system. So the idea here is to have multiple sensor modes on the Kevlar straps, but the output of the sensor mode is then connected to the wireless Bluetooth hub, where the Bluetooth hub transmits the data to a base station. Each of these sensor modes comprises of a printed capacitive strain gauge and a relaxation oscillator. The relaxation oscillator employs a Schmidt trigger, and the output of the relaxation oscillator is a square pulse, whose oscillation period is given by this equation. We can see that there's a small nonlinearity that is the parasitic capacitance of the interconnect. Once the parasitic capacitance is compensated for, we will have a highly linear relationship between the oscillation period and the capacitance. So we established that the sensor mode has a digital output whose frequency is varied with capacitance change. The frequency is determined by the microcontroller on the wireless hub by counting oscillation pulses. And for rapid tracking of strain, the system is sampled at 100 Hertz. Due to the digital output of our sensor mode, we don't need an excitation signal, or which makes us not need an ADC on the wireless hub. Also, any kind of interference that might be caused due to the long wires on the Kevlar straps with approximately 2 meters is reduced, whereas an AC analog signal will be susceptible to any kind of interference. So the overall system was implemented by using a low power Schmidt trigger that consumes 1 milliamperes at 3.3 volts for oscillation, for 15 kilohertz oscillation. And the Bluetooth SoC uses NRF52840 Bluetooth SoC that is a 64 megahertz CPU and a Bluetooth 5.0 radio. The Bluetooth 5.0 radio has a coverage range of 240 meters or 800 feet, which is plenty enough to cover the entire space habitat. Also, the entire system was powered through a 3.7 lithium polymer battery that consumes, taken this together, we have the wireless hub that consumes 7.6 milliamperes, giving us a battery life of 15 hours. So taking the sampling rate of 100 hertz and the clock rate of the Bluetooth SoC, we have greater than 75 dB of dynamic range. So here's our test fixture. We can see the sensor mode and the wireless hub is connected together and attached to the Kevlar strap. And this system is powered through the lithium polymer battery. To validate the linearity of our oscillator, we measure the oscillation period using discrete capacitors that were above the range of the capacitance of the strain gauge. So in this point, we can see that there's a non-linearity initially. This is due to the passive capacitance, which we accounted for was approximately 5 picofarads. So here is our plot after the compensation for parasites. There's the limitation, and this limitation is due to the microcontroller clock rate of 64 megahertz and the sampling rate of 100 hertz, which means we cannot calculate the capacitance that's low in the lower range, that's in femtofarads range, or capacitors, higher capacitance, that is to say, like in microfarad range. And to account for our oscillator sensitivity, we determined the jitter to be about 143.8 nanoseconds at 15 kilohertz, which gives us a 28 femtofarads of capacitance resolution. And for real-time strain measurement, we used an MTS or material test system and a dog bone tensile specimen. The ends of the dog bone tensile specimens is attached to a hydraulic grip that has an actuator underneath it for strain exertion. And the tensile strength is an aluminum tensile specimen is an aluminum ATSM AS6061 tensile specimen. And the printed capacitor strain gauge is printed on this structure. And the lead wires that connect to the oscillator has its own inherent 52 picofarads of capacitance. So the principle of the strain gauge is given by the principle of strain gauge capacitance is given by a Nanotechnology 2013 paper. We see that the capacitance is inversely proportional to the distance between the electrodes, which implies that as the strain increases, the distance between them increases, therefore decreasing the capacitance of the strain gauge. This theory is experimentally proven by this plot. We can observe that at low strain, the capacitance is high, and at a higher strain, the capacitance is low. To validate the wireless multi-channel data acquisition, we imitated the sensor mode using MATLAB and a function generator called Analog Discovery 2. With the help of MATLAB, we created pre-generated lookup tables for the clock frequencies that were then fed into the function generator. The output of the function generator was used as the input to the wireless hub. So the output of the wireless hub is pictorially represented in this figure. We can see that it is the frequency change over time to represent the oscillator's frequency change. So other patterns here are used to represent different rates of strain. So overall, to conclude this presentation, structural health monitoring is an essential means to ensure safety and structural integrity of a structure. Printed capacitive strain gauges is a promising technology for structural health monitoring or Softgoods, and they can be extended to other applications as well. And our structural health monitoring system employs a capacitance to frequency readout and has high linearity and dynamic range, and is designed for distributed and wireless sensing. And our system is optimized for the use with Kevlar straps, but can be scalable to higher channels via multiple hubs. And that's all I have, and thank you. Any questions?